Hi everyone. My name is Manuel, and today we will dive into cache memory techniques and we'll be exploring on how caching helps CPUs work faster by managing memory smartly. And this is crucial in both computer architecture and then system performance. So let's dive into it. Okay. So the question is, what is cache memory? So you see, cache memory is a very small high-speed memory located. You see, it is a very small, it is very small and a high-speed memory which is located closer to the CPU. So its main purpose is to reduce the time the CPU takes to access frequent use data. You see, so you think of it as a mini workspace. So you see, instead of you walking to the storage room every time, you keep what you need on your desk. So you see, and it fits in the hierarchy like this. You see, we have the registers are faster, and they are followed by the L1, L2, and then L3 uh, cache memories. You see, then the RAM, and then the final storage, or finally the storage. So you see, the registers they follow like this: the L1, L2, L3 before your RAM, and then the disk. So we'll explain this later. We'll explain this data when we keep going. So why cache memory matters? You see, your CPU, your CPU process instruction at a very high speed, but RAM is much slower in comparison. So without a cache memory, the CPU will spend more time waiting than working. You see, since your memory is much slower. So the caching minimize the gap by storing recent or frequent use instructions or data closer to the CPU. So that means your frequent use data are stored in your cache memory, you see, so that your CPU will not have to be waiting or going directly fetching your instructions from the memory. Instead, it will fetch the instructions from the cache memory. Since the memory is a bit slower, the some of the instructions will be stored in the cache memory to it and it also help your CPU to work faster. So these are some of the these are some of the cache memories we have. So we have the L1. So for the L1, it is closer to the core and it is faster, but very small. It's very small. So you can see the storage is from 16 to 64 kilobytes. You see. And then we have the L2. For the L2, it's a bit bigger. Yes, it's bigger, but also it is slower than the L1. And its storage size is around 256 kilobytes to 1 megabyte. And then we have the L3. You see, for that one, it's shared among multiple cores, like largest and slowest of the three. So you see, this level, it ensures a balance between speed and size. Yes, it ensures balance between speed and size. And also, we have the cache mapping techniques. So the cache mapping techniques, you see, to store memory data in the cache, we need a system called mapping. And these are some of the mappings we have. We have the direct mapping, the fully associative, and then the set associative. You see, so each offers a different trade off between simplicity, flexibility, and then speed. So let's talk about the direct mapping. So you see, in this modeling, each block in the main memory maps exactly one cache line. You see, each block in the main memory maps to exactly one line. So it is very fast and easy to implement. But there is some downsides. Like for instance, if two frequent use block, sorry, let's say if two frequent use blocks map to the same line, they will keep replacing each other. That's a conflict, you see. So, but what you have to know about this is like each block in the main memory, it only maps to exactly one cache line. Okay, and we have the fully associative mapping. So in every memory block, uh, so any memory block can go into any cache line. You see, you remember the direct mapping, it can only map to exactly one cache line. But for the fully associative, any memory block can go into any cache line. So this avoid conflict completely. you see, but it is costly. Like the hardware needs to check all lines to find a match, which can slow things down, but it's quite expensive. So we have the set associative mapping. So you see, this type is a hybrid approach. So the cache is divided into set, which is a memory block maps to a specific set, but it can occupy any line within the set. You see, it can occupy any line within that set. It reduces conflict whilst keeping the lookup process efficient. See, for this, it reduces conflict, and also it is the hybrid type. And then we have some of the common configurations, which is the two-way, the four-way lines and stuff. So you see, this refers to how many lines per a set. The two-way and the four-way, they refer to how many lines per set. So we have the cache memory, the cache replacement policy. So for the cache, you see, when cache is full, we must decide which block to remove to make space. So the LRU, the LRU, it evicts the block that hasn't been used for the longest time. So like the least recent used. So let's say if that block is not used frequently, it will be evicted. And then we have the FIFO. So for that one, it removes the oldest entry. So first in, first out. So it removes the oldest entry. So if you enter first, you go out first. And then we have the LFU. LFU, it removes the least accessed block. You see the least recently frequently used. So if it is not being used regularly or frequently, it will be removed. And then we have the random replacement. For the random replacement, it pick any block randomly. So surprisingly effective in some cases. Yes, it just pick any block randomly. So it can pick any other one at all. So we have the cache write policy. So you see, the cache write determines how data is written to the cache and the memory. So the cache write policy, they determine how data is written to the cache and the memory. So these are some of the examples. We have the write through. The write through, every write updates both cache and memory. So it is much safer and slower. You see, every write updates both cache and memory. And then we have the write back. For the write back, only cache is updated immediately. For the write back, only cache memory is updated first, and then later the memory itself will be updated. You see, but we have some downside of this. You see, sometimes it is quite risky if in case power fails. So let's talk about the cache coherency, which is the multiprocessor. So in multi-core system, each core may have its own cache. You see, but the challenge is if two cores have a copy of the same data and one changes it, how do we keep them siding? You see, so like the protocols such as the MESI, which is the MESI, and then the MOS, the MOESI, they solve this problem by managing the state of each cache block across all processors. You see, so they manage each cache block across all processors. Then we have the performance matrix. So the performance matrix, let me try and explain this in my own way. So you see the hit rate. The hit rate is how often the CPU finds the data in the cache. Do you get it? So the hit rate is how often the CPU finds data in the cache. And then the miss rate is like the opposite of the hit rate. You see? So the miss rate is the opposite of the hit rate. And then the miss penalty is the delay caused by a miss. See, so the miss penalty is the delay caused by a miss. So we see um, um, the total delay is given by the hit time plus the miss rate times the miss penalty. So that gives you the total delay. And then so how do we improve cache memory? Or how do we improve the cache performance? So here are some of the ways to make caching smarter. So you have the perfection. So the perfection, that means it will load data before it is needed. The perfecting will load data before it is needed. And then we have the victim cache. So the victim cache, it will temporarily store recent evicted blocks in case they are reused. So it will temporarily store recently evicted blocks in case they are reused. And then we have the multi-level caches. So the multi-level caches, they are the L1, the L2, and then the L3 hierarchies. And then we have the way predictor or the way prediction. So they predict which cache way a block will go into. So whenever a block is available, they will predict which cache way that block should go into. And then we have the real world example like the Intel and the AMD CPUs. You see the Intel and the AMD CPUs, they uses the L1, L2, and then the L3 cache in modern CPUs. So they are mostly used in the modern CPUs. And then we have the ARM processors. So they are mostly used in our phones, which uses efficient caching for low power. And then we have the gaming consoles and saver. For them, they rely on smart caching for performance. So the summary, let's summarize everything up. To wrap up things, you can see that the cache bridges the speed gap between CPU and the RAM. The RAM. So this is what you have to know, that the cache memory, they bridges the speed gap between the CPU and then the RAM. And the mapping and the replacement strategies matter. You see, different mapping, replacement, and write strategies, they help balance the speed and the cost. Yes, they help to balance the speed and the cost. And then the smart caching. The smart caching is critically for high performance systems. They are for high performance systems. Okay, so this is the end of our lecture. And thank you so much. We will meet another time.